think we're just on time. Oh, my mic's good? Yeah, okay. I think we're on time here to get started again. Just a couple of wrap-up things there. Just want to acknowledge the whole group from AFRL, because I said Fred Schauer, and he's so humble. He came by and says, no, it's my whole group, man. So why don't you guys from AFRL, wherever you are, just wave a hand for us that are working many of these RDE issues, because they've been great to work with, and I really appreciate all their help. So thank you guys. And during the break, we had a discussion, and I said, if anybody knows any applications, constructive applications for detonation, let me know. And so they came over and gave me a few that I didn't know about. So it's kind of fun. I put them on the board over there so I wouldn't forget. There's actually a plating process that sprays solids where you use the detonation to stick that to a material. It's really a very interesting possibility. I knew that had been tried. I didn't know it had been actually commercialized. There's a stamping process. That I didn't know about at all. You know, you can obviously use a detonation to do a stamping process. And then there's one for actually, you know, fracturing rock, right, that's used. I think that one is just in Russia. I don't know that's practiced here in the U.S. And then down on the very bottom, tire shredding. Now that'd be pretty interesting. I had not heard about that before, but it'd be a great way to, you know, take a discarded tire and get all the material out of it, right? Because you got all those metal cords. Any a comment on that one? Go ahead.
Well, let me add one more. They do cleaning of power plants. They run a detonation.
Oh, yeah, soot blower. I guess, yeah, and that one I'm familiar with. I guess I never thought of it as an application of detonation, but you're right. When you do soot blowing, that is. Yeah, so there you go. What's that? Soot blower? Is not. Through the inside. See, I didn't know that. That's really an interesting point, so thank you. Thank you. Anybody else know of any? Go ahead.
There's a Mythbusters where they use dynamite to clean the inside of a cement truck.
Now that sounds like fun, but yeah. Well, let's jump into. Oh, go ahead. One more. Okay. Oh, okay. So I didn't know all these interesting, useful applications of detonation. So there you go. We learned something. I learned something today. Well, I'm going to move on now, and we're going to jump into kind of the last session here for new developments. And this is going to be, you know, a little bit different than probably other things you've heard. And the title there, Making Oxy-Fuel Combustion an Efficiency Advantage. Yesterday we talked about oxy-fuel combustion and how that would actually be a way to achieve carbon dioxide separation because you don't have any nitrogen in the process, right? So you could get to, you know, a thermal energy production where you'd have just CO2 and water in the exhaust stream. So we'll take a look at that. The picture that you see in the inset there is an oxy-fuel flame that we're using to study conductivity in an oxy-fuel flame. So we'll talk about that a little bit later on. So this is the last point, you know, that we're going to cover today. And I'm just going to have a little bit of a quick review here of a slide you saw yesterday that talks about the energy penalty connected with making oxygen for oxy-fuel combustion. Remember, I went through and just said, look, if you were going to do a pure oxy-fuel combustion, you'd have this air separation unit in the process, and that's going to consume some energy to create that oxygen. We went through the energetics of that and find out, you know, it's going to take roughly, you know, 1/10 of the energy of an efficient power plant to make the oxygen you need to actually run the power plant. And so that's where all the penalty comes from in terms of capturing CO2 using oxy-fuel combustion. Now, in a conventional approach to doing oxy-fuel combustion, after you go over and make that pure oxygen, which costs you a lot of energy, what's the next thing that you do? You dilute it with CO2 or water, something from the, you know, the flue gas. It can only be CO2 or water because you want to condense the water out. So you went through all the energetics of making oxygen just to dilute it again. You get no advantage at all other than the fact you'll have pure CO2 in the exhaust stream. So that doesn't sound like the best thing to do with pure oxygen. So what else could you do? Well, there are a number of industries already where you use pure oxygen and you use it for some advantageous reason. All right, if you could find a way to make extra power because you had pure oxygen, then oxy-fuel would be an advantage. You already do that in certain industries where you want high temperatures, like glass making or steel making. You use oxygen there. And you already use oxy-fuel in rocket engines, right? Some rocket engines, just because you can get to higher propulsion with that. And so can you do this actually in power generation? There's a way you can take advantage of that pure oxygen in a power generation application. Well, let's take a look at how you might start to think about that idea of using pure oxygen in a combustion process. You know, I'm showing here a plot of efficiency against temperature, and there's the, the Carnot efficiency if it's a heat engine. Then I'm showing plots of different technologies that we already have today. Existing subcritical coal plant, about 40% LHV efficiency. The supercritical, a little bit higher. Here's a simple cycle gas turbine, and then finally a combined cycle gas turbine. And I'm plotting the peak, working temperature, the temperature for the working fluid along this axis. So, gas turbines up to about 1700 Kelvin, right in this range, at least for ground-based power. But if you have oxy-fuel combustion, all right, you can get to very high temperatures, right? 3000 Kelvin. It's enough to melt steels and other things. So, how do you actually use that? I mean, as a working fluid, it's an interesting question. Is there a way you can take advantage of that? Well, there is. All right, and you probably have heard about this, at least historically, or maybe seen it in textbooks, looked at magnetohydrodynamic power generation. The high temperatures that are possible with oxy-fuel could actually run MHD, or magnetohydrodynamics, as a topping cycle, and it's because you have oxygen that you can run this cycle. It's going to be a combined cycle because you take the exhaust of that combustion process and actually then add it to a bottoming cycle. So how does it work? Well, you remember even a conventional generator operates very simply. If you had like a copper wire and you push it through a magnetic field, that motion through that magnetic field pushes the electrons out of the end of the wire, right? Just due to the Lorentz forces, you push that in there, and that's how a conventional generator works. You spin the wire through a magnetic field, and you generate electricity. Well, if you had a conducting gas, it'd be no different than taking a wire, right? And so when you pass that through a magnetic field, then you have this, electric generation that you could get from collecting the current from that gas, just as if it was a wire moving through, with motion through that magnetic field. So it really isn't any different than things that you're familiar with about how you might generate electricity. You use motion in a magnetic field to generate electricity. So if you did this in a power cycle, again, as a combined cycle, this is what it would look like. You would have an MHD power unit take some of the energy out of that high temperature part of the cycle, use it to create the oxygen, all right? Any leftovers then become output work for what you want to do externally, and then the combustion products at high temperature would then drive a steam boiler as a bottoming cycle. So you can actually work out, and for reasons we'll get to later, at least with technology we know about, you can only get to maybe like 2600 Kelvin at this point and have a conductive fluid, so that's why you're forced to go to a bottoming cycle. We'll talk about that later. So you're going to make this combined cycle, and you have to then calculate, well, what's the type of efficiency that I could get from combining these two processes? So for example, if the efficiency of this topping cycle, accounting for the fact I've got to take air and run it over to the separation, or energy and run the separation unit, if the efficiency of that topping cycle is even just 10%, then I combine it with a bottoming cycle that's 45%, which is representative of kind of advanced steam cycles we know about today. I can do the combined cycle efficiency, and you can work that little equation out there, and show you got an efficiency of about 50% just for these numbers that I've put here, which are reasonable numbers. We could actually achieve higher efficiency on that topping cycle, maybe. I don't know that yet. We're still trying to sort out how high you could go at that point. But 50% efficiency with inherent CO2 capture. Remember yesterday we were talking about chemical looping. I said, well, what's a drawback of chemical looping? Well, you can't go any higher than the steam cycle temperatures. You need some combined cycle, right? Well, this doesn't have that limitation, right? I can get to higher efficiencies, directly with this technology. I have direct CO2 capture and potentially very high efficiency. this is not a new idea at all. It's been around a long time, and it was aggressively pursued more than 25, 30 years ago in the 70s and 80s. The Department of Energy had a fairly large program on it, as well as the Soviet Union. And you know, both of those activities resulted in electricity being transferred to the grid at some level. Particularly the demonstration in, this was actually in Moscow, I'm told. It was 25 megawatt is the one you're looking at, and you can see the tube where they're actually doing this MHD. This one actually used natural gas fuel and actually accumulated a lot of hours, as we understand from the literature. The downfall to this as a technology, at least particularly here for the U.S. program, was the materials for the electrodes. Got a very high temperature, you know, system operating, and the short electrode life, and also what we'll talk about later, the seed material use, kind of hamstrung the technology relative to other things that were being pursued at the time. All right, and that's an important understanding. People looked and they said, well, look at all the issues I've got to address with this technology. I could build integrated gasification combined cycle. And that's pretty much the way things developed over the next 2 decades. We pursued other things. I'm suggesting this might be worth a look again because the issue has changed. We now have to worry about carbon capture. There's already people that are building oxy-fuel combustion systems, and a lot has changed technically over the intervening years. I tried to put this on a slide. You know, this is a slide I'm showing to people who think about planning programs to make the point. There are a lot of things that have changed since that legacy effort to understand MHD. I already said at that point, no one was thinking about CO2 capture. Today, it's a main driver. And people have already developed oxy-fuel combustion for large boiler applications. It's already a technology that people have been thinking through, are trying to deploy at different levels. At the time this earlier program was pursued, the way you would do technology development, do a large demonstration. Well, you know, those get really costly, and that's where I think there's pushback to this as a technology. Again, it's like you're not saying we're going to need to go and spend that money to just do another large demonstration. But you think about the developments that have occurred in simulation and our ability to validate with smaller experiments, it's probably worth looking at this again and focus on, well, let's put validated models for different concepts together, not just demonstrating every one of these. The earlier program, the way they achieved high temperatures was just by preheating the air, because they didn't want to suffer the penalty of all that oxygen. But today, people are already using oxygen production with much more efficient ASUs, 40% better since that earlier program, because there's an interest in doing oxy-fuel combustion today for CO2 capture. So the situation has changed. At that point, the biggest pollutant issues were SOx and NOx. All right? And so there was a lot of concern in the economics for this MHD process. What are the economics of the SOx and NOx removal in that process? Well, if you're going to do oxy-fuel combustion, you still have to worry about these things for coal, but it's not done with traditional pollutant controls. You're trying to capture all the exhaust stream and condense the water out. There's actually today a process, the gas processing unit downstream. You're going to run the whole flue gas through that, condense it down, and then you're going to be able to handle those emissions in a much different way than in that legacy program. At that time, getting a 6 Tesla magnet was a chore. All right, been a lot of developments in magnets. I'm told we could probably get a much higher strength magnet today than we could at that time because that technology has changed a lot. Back then, people were looking at analog electronics to do all the controls. Again, today, we have solid-state devices that can handle actually very impressive power flows. So can we see a change in that regard as well? One of the things that we'll see later that's important is, can we turn off like an unwanted arcing event in an electrode? We just couldn't do that with the analog electronics, couldn't detect it, couldn't diagnose it. I think we could today. I don't know that for sure, but we do similar types of processes and control for other things that we're interested in. At that time, the only real focus was on something you'll see in a moment, linear generators. We could look with computational models at a couple of different geometries, and something that we're going to try to do. One of the things that's really changing very rapidly right now, at that time everything was done by conventional manufacturing. Well, if you've been following what's going on for advanced manufacturing, it's really very impressive, how intricate designs can now be manufactured with additive manufacturing with different material sets embedded in the same structure. So one of the questions that we've started asking is, could we use advanced, manufacturing techniques to put in graded electrode designs that we'd manufacture right into the MHD tube? I don't know the answer to that, but it's a research issue that we're going to start taking a look at. And this is one of the things. It's why I'm very interested. I'll be meeting with some colleagues here in the front row from the Princeton Plasma Physics Lab. At that time, the conductivity of the gas was entirely achieved by seeding the flow, and we'll talk about that later. I keep thinking there's got to be a way around that to get the flow to be conductive enough. There's people that have proposed using nanosecond pulse discharges to ionize the gas. Some of the fast electronics enable you to do that. They weren't available at that time. Maybe it's worth a look. So these are some reasons why, as a lab, we started to look at this. Believe me, we've got people say, that we've looked at that 20, 30 years ago. It doesn't seem possible. So I'm saying, but I think it might deserve another look. And so we're having actually a healthy discussion about this. We've gotten good support internally to start taking a look at these issues and say, can we take a step here and really turn this into a technology that's viable in today's context? So let's keep going here. Even if MHD, direct power extraction of technology, doesn't emerge as a contender for power generation, it's important for all of you to have an introduction to just plasma in general, because it's important for things that a combustion engineer is interested in. This review article shows some work that's going on actually right here at Princeton, looking at how you can achieve ignition in very demanding applications by exploiting some of the ionization chemistry that you can put into the flame. There's a couple of papers on this that this review article covers that are quite interesting, so I'd recommend it as a good starting point. Another thing I thought's interesting, I had a discussion with Bill Green about this at lunch. There have been a couple of recent papers that actually surprised me very much, particularly this one by Drews up here, 2012. They're using AC fields on flames, and they can actually observe macroscopic changes in the flame structure. And I'll have to be honest, because I worked ionization in flames quite a number of years back, and we had difficulty seeing any impact on the hydrodynamics of flames from the DC fields that we were putting in. And you can show that you'd expect that just from a simple, force balance on the flame. But this paper showed that with an AC field input, you can get a quite different result. And so it's an interesting recent paper that says maybe it's worth looking at, ionization in flames. We actually built ionization sensors that we did diagnostics in practical combustors with at our lab. We have one of those patented and almost reduced it to commercial practice. Didn't quite make it into the engine stage. But so there's some things to understand about how flame ionization can be used for diagnostics. And there's some very far-reaching propulsion concepts and even electric thrust propulsion that depend on understanding the basics of plasma. This one down here, I've shown it schematically. It's quite interesting. It's called the MHD bypass concept. And this is for people who are worried about how do you fly at Mach 7. The gas is going to come in there and go through the first shock and be extremely hot. So it's just too hot to burn any fuel, so you have to take some enthalpy out of there. And one of the ways you could do that is pull the enthalpy out with MHD and then stick it back in at the back end. Well, that's an interesting thought. Is that practical? Could you put that on a propulsion vehicle? Well, people are looking at it, but I just want to point out it's something to be aware of that relies on the same technology. And even if you decide, you don't want to work in, combustion or propulsion, non-equilibrium plasmas are really a key technology for a lot of things that are components of modern, life, modern technology. Plasma TV is the easiest one. If you just want to see kind of the breadth of things, go back in and look at this National Academy's report, because it talks about lots of different applications for plasma technology and plasma science. So, all right, so we'll talk a little bit about this, just giving an introduction to how magnetohydrodynamics works. Probably from your undergraduate physics classes, you remember these very simple fundamentals for electromagnetics. Electric field, it's a vector. The units here are volt per meter. It can be described from a potential, the negative of the gradient of the voltage. And so in 1D, the field is just the voltage divided by the length with a negative sign to be consistent. So that minus sign means that the electric field points to low voltage. And then the magnetic induction, the B symbol there, it's also a vector with units of Tesla or volt seconds per square meter. And probably everybody knows or remembers that the force on a charge inside of a magnetic field is just the charge itself times the electric field right there. And so that's how you define the electric field, the force per unit charge. You have to reach back a little bit in your undergraduate physics. For a magnetic field, it's a little bit differently. The charge times the velocity of the particle with the cross product of the magnetic induction B. So for example, what I'm showing here is a charge moving along this axis. There's its velocity, u sub q. There's a magnetic field in this direction. And so if you just take the cross product, and I always have to do this with my right hand to get it right, go like that, you'll find the force on the particle is actually pushing down the way I've drawn that diagram. So that's how the magnetic field puts force onto that particular charge. And so really important for the rest of this talk, I'm going to define the net electric field as the combination of the electric field that exists from some distributed charges as well as the velocity of the charge we're interested in, cross product with the magnetic induction right there. So that's the net field, and that's the nomenclature I'll use as I'm giving the talk today. So how do you make a generator? What do you actually do to actually create power from a conductive gas that's flowing? So this is an example of an MHD channel, real simple here. The flow, the conductive gases are flowing along the channel in this direction. I have a magnetic field running along this axis. You can see it right here from that vector. So U cross B points down in that direction. And so that U cross B is what creates the electric field that you can use to drive a circuit out in this region. And how is that similar to a conventional generator, something you're familiar with? Well, if instead you just imagine taking a wire that touches this end and this end, all right, top to bottom, and you just push it down there, right? It's just a wire passing through that field, and you would generate electric current that way, or you generate potential, and you drive that potential around the circuit. Okay, is that straightforward enough? That's how it works. It's no different than a conventional generator. It's just instead of a wire moving in that direction, you've got a gas just flowing down through that magnetic field. So how much current can you get out of that device? And this gets a little bit detailed in the next couple of slides, but we'll come back up from it in just a minute. Well, the current flux is proportional to net field. All right, there's the flux J, current per unit area. That's the conductivity of the particular media interested, and that's the net. Remember, I defined that a moment ago. And also for nomenclature, E naught, where I put that sub-zero, is applied by the external load. So that's the electric field that's associated with the current that's flowing around the circuit on the outside, and it doesn't include the magnetic induced field. And that's an important understanding. So that E naught, that's the voltage. For example, if I had a battery and connected it to a resistor, it's the voltage drop across that battery, or across the resistor, which is the same as what's across that battery. Okay, so I want to make sure the nomenclature is clear as we work through this. So here's the expression again then, the current flux, the conductivity times the net field. So now I'm substituting for the net field the combination of what's applied by the external load, E naught, plus what's generated by the interaction of the magnetic field with those charges. So I'm showing both those vectors right over here. The external field, the points this way, the E naught, that's due to the current flowing around that resistor. And then the field that I'm generating from the motion of that gas is pointing in this way. And so the current that flows is a result of the difference of those two fields times the conductivity. And so there you have the expression. So in other words, my external field is essentially applying, my external load is essentially applying a field. My motion through the magnetic field is actually generating a field at U cross B, and it's the difference of those two that drives the current. Now there is an internal resistance we'll get to here in a minute, and I'm just showing this oddly disconnected, because it's sitting right in the gas flow where you're also generating, but we'll show what that is here in just a minute. You can work through this algebra you know, and see that this external load, the gradient of voltage, it's 1D, so it's the difference in voltage divided by the distance across that gap, which is B. All right, so I have an expression for this particular field, E naught, and that equals the current times, well, it's not pointing, the current times the load resistance. That's just from Ohm's law. So all I'm telling you here is the voltage difference across here, high to low, sets up this electric field across that region, and then I also have generation from that U cross B term right there. So if just for convenience, the open circuit resistance, if I have an open circuit, RL is infinite, J is then 0, and it implies at open circuit the voltage across here equals what you're generating from pushing the material through that field. Okay? So I think that makes sense, right? If I'm saying I have an open circuit, these two vectors have to be equal to each other. That's all I'm saying. You're pushing it through, you generate a voltage across that region. If I start putting a load on, I'll actually change that. The current that's going to flow is the UB, the open circuit voltage, divided by both of those resistances. All right? So this is the same kind of stuff you study in freshman physics for like how a battery works. The open circuit voltage divided by the internal resistance and the load resistance. So just to make that last point clear, a different way to state what I just covered there. All right? I have the generator here. I have an open circuit. I have this vector, which is the applied voltage, which happens to be the open circuit voltage, and it exactly balances what I'm generating from the motion of the gas through that channel. If I go to the other extreme and I just short the thing out, right, then there's no voltage between these two plates, right? They're the same potential. So that means this field is now 0, and the only thing I have is the UB that's driving the current, and the only thing that's opposing it is the internal resistance. All right, so that's kind of the two extremes, the open circuit and the shorted. And the key point on this slide is I can actually control the voltage from here to here by deciding what load I'm putting on. If I can control that voltage, I can then affect what this E naught term is, which is the case in the middle, where I put a resistance RL and I have a particular field that exists across that region. So you have, you know, these different extremes in the case where you're actually generating power there in the middle. So this is an electrical analogy. I'm just repeating the same thing one more time because I know it's hard to grasp this first time through. It's just like a battery where this is the MHD generator with a certain open circuit voltage, the U cross B term. This accounts for the gap across there that gives you a voltage from the field, which is UB. There's an internal resistance connected with passage of the current through the conductive gas, and then you have a load resistance on the outside. Most of the literature you read will define this load parameter K. It's the voltage across the load divided by the open circuit voltage. You can then just work that out. The voltage load is I times the load resistance, and then the open circuit voltage is I times those two resistances added together. So K has this definition or this definition, which is a ratio of two powers, or a ratio of resistances, or finally a ratio of the open circuit field and the generated field. So different ways to define this thing load parameter, but you'll see it all over the literature, so you want to know that's what it is, different ways to define that load parameter. And you actually find that load parameter useful to think about how much power is actually generated in one of these devices. So the power that actually goes over to this load is the current times the load voltage. So here I am with the current is just the area times the current density. I plug in the value I just gave you for the current density itself right there, and then I have my expression for current. The load, again, is the voltage across the load. B times E naught comes from that UB term I just presented along with the factor K. So I jump right down to the bottom, put those together, and you have an expression for power density. Even if you didn't follow the development here, this is the key point. The power density you get out of that tube is proportional to the square of the velocity down the tube, the square of the magnetic field, and then load parameter, how much juice I choose to pull out of the device. All right? So even if I lost you, I had to go through this quickly in terms of like, here's how we develop this. The power density itself is proportional to the square of the velocity and the magnetic field intensity. Well, the velocity I can control and make it high, right? I can push the gas through there. I said before, we're getting progressively better at making high power magnets, and the power density goes up as the square of velocity and magnetic field intensity. So I'm starting to think, it's interesting to look at that as we get more powerful magnets. So that's the key point of development up to this point. So I'm going to go just a little bit further into maybe some of the details. I know it's not easy to grasp a bunch of math, but I'll try and summarize it quickly with the physical implications. But here's what I just said. There's a current flux along the y direction in that generator that's the difference between my load field as well as what I'm generating, and that's how that simple generator works. What you're going to hear in the next couple of slides, even if you can't follow the math as we quickly move through this today, the key thing is physically what is going on then as that current flows through device, because you're going to actually find you don't get as good a performance as what I just described. Instead, there's some other things that get involved from the Hall effect, and so we're going to take you through that on the next couple of slides. So here's the complications that arise in terms of generation in these devices. In most of these MHD applications, the charge is carried by the electrons, right? The cations that, you know, those electrons came off of, you can almost imagine it like in a real conductor where they're pinned down inside of the lattice. Here they're not, they're free to move, but they can't move very fast. And so the electrons are doing all the charge carrying, you know, as that thing moves through the magnetic field. By convention, of course, those electrons are moving against the electric field. And the current flow itself has an associated charge velocity, which I'm designating with a small e subscript. So I've talked about the flowing gas running this way, but as soon as the electrons start to move to complete the circuit, well, now they're moving relative to a magnetic field, and once again, they experience a force from the magnetic field. So it's interesting, the actual flow is carrying them in this direction. The U cross B that I'm applying from that flowing motion tends to drive those guys up in the diagram I've shown, but as soon as they start moving up, they feel the magnetic field, which pushes them by a cross product backward or forward. I'm sorry, I can't remember. I'm sorry, this way. All right, so this way when you do the cross product. And so now you have to worry about how does that affect my electric field. All right, so that's the Hall effect. And as I've shown here, then the actual motion of the electron, you know, comes out like it's tilted. And so how far is it tilted? And by the way, you know, this is a simplification. The actual motion is not going to be straight up, but it just helps you understand what I'm talking about with this Hall field. So that's something we got to account for. So, you know, if you want, you can go home and, tonight, I know you're just dying to sit and do algebra tonight. And so here's your chance, all right? You can go through and do this and do some ciphering. But the velocity of the electrons in a field, that's their mobility, the net field, plus their motion cross B. This mobility can be related to the conductivity. Assume the B field is just, you know, pointing out of the page the way I've got it drawn here. And then you just write an expression for the electron velocity itself here. Plug in these terms. This is actually very straightforward to do. So we're not going to take you through it, but I mean, literally, it's just a page of algebra. And you'll find out that the current density that's flowing along the x-axis is given by this expression, which depends on that electric field as well as the magnetic field. And then there's the current flow in the y direction that we're trying to collect to make power. So they're given by these expressions. So let's see what that actually means in practical terms. Here's a simple generator. It's the one I've just showed you, but now I'm going to account for this Hall effect in terms of analysis of that thing. So here you just have big conductive electrodes running along the axis of the flow. Flow is going this way. If I use the expressions on the past page, the previous page there, the electric field running along the x direction is 0, right? Because I just have a big conductor running along the x-axis. You can't have a field there, right? Because that conductor is going to just make it the same potential everywhere along the x-axis. So no field running along x. If I plug into the equations I had on the last page, I can get an expression for the current that goes from top to bottom. And here it is, conductivity, this term on the bottom, times the net Y field, which is something we saw before, a couple slides back. The net electric field minus that which is from the magnetic motion. So this expression over here is the same as that simple generator analysis we gave without the Hall effect. That was this term right here, no Hall effect. So compare this to this. So the difference is this quantity down at the bottom, 1 over 1 plus mu e squared b squared. And so this is the effect that you get from that Hall effect, you know, where the electron motion, as you're trying to get current to go upward, is interacting with the magnetic field. It cuts down the amount of current by this quantity, you know, right here. And then there's also a current that flows along the x direction. Again, you go back to the last slide, you plug in the numbers with the electric field running along x equal to 0, and you'll come out to an expression which is this term times one more quantity, mu e b, times the current that's flowing in the y direction. So look at this mu e b thing right here and here appears in both of those equations. It turns out it's a parameter that controls how big are these effects from the Hall effect. And so you need to know how big is that quantity, mu e, which is the mobility, times the magnetic field. And this gets really into the detailed physics of plasma here. Well, not too far. So you can actually calculate that magnitude of the mobility times the magnetic field. And that just comes from a simple force balance for an electron that's moving. All right, you have an electron moving in a magnetic field. There's the mass of the electron, the rate of change. The electric field is acting on it with the charge times the x direction of the field. You can replace this derivative just by some mean velocity divided by a time scale, the time scale between interactions. But you can also write, all right, because this thing's going to collide, an electric field times a mobility equals some mean velocity. All right, you can go in and look this up in introductory books on plasma. You combine those and you have an expression for mobility that's the product of the time between collisions and then the ratio of the charge divided by the mass. So that's just a quick algebraic development that's based on just, you know, a simple force balance. You can also express the magnetic field in terms of a cyclotron frequency, omega, and this gets interesting if you don't work in this area. It's not what you'd probably think of initially, but don't forget that electron is sitting in this field, and as it's moving, the magnetic field is always acting on it at a right angle in that plane, and so it will actually just go in a circle, all right, at a certain frequency, omega, and you can work out what that frequency omega has to be just by balancing the forces between the magnetic field B right here and the velocity of the electron, and it'll just go in a circle. So if it had motion in one direction, it'll spiral along that direction because the magnetic field is going to keep moving it in a circle. So it has a particular frequency called the cyclotron frequency. There's the value of it. Combine that expression with the one above for the mobility, and you get this term mu e times b equals the frequency times the time between collisions, and that's called the Hall parameter. So I hope I haven't lost you too bad here yet, but on the last slide, the mu e times b, that was the quantity we were interested in, appears in a lot of these equations, and it has this definition of the Hall parameter, omega times tau. And now here's where the physics are. Physically, what that's saying is if omega times tau is a big number, then there are a lot of cycles before you run into another particle, right? All right. On the other hand, if it's very small, then there's lots of collisions before a cycle is complete. So that's physically what it means, all right? It's independent of the details of development. That's what that Hall parameter is all about. So let's go back and see what that means. I gotta make sure I didn't skip. Okay, one more slide here. So let's go back to this actual generator itself. So I said that mu EB is this Hall parameter omega tau, and I'm going back again to this example. So the current is sigma times mu times this difference, and then 1 plus this parameter, the Hall parameter, omega tau squared. That's the mu EB that we just saw. There's the Hall parameter again, connecting the current density along the y-axis with that along the x-axis. So for practical MHD devices, this Hall parameter is somewhere maybe between 1 and 10. What that's telling you is if I have a Faraday generator, which is this design where I just have 2 big electrodes, all right, there's a significant reduction in the current that's flowing from here to here due to this Hall parameter compared to just my simple understanding where I ignore it. All right? So I've just taken you through all the math just to get to the physical part of this, that when this parameter takes on a range of values, it affects the current that's going to flow in this direction, which is the stuff that you can recover and do useful work with. And this lets you calculate how much you're affecting that due to this Hall effect. So it's not insignificant is my point, right? If you had a value of 10 right here, 1 plus 10 squared is 100 and 101, wow, you've really cut down the amount of current that you can extract for useful work. So you have to pay attention to this Hall parameter and the Hall effect itself. The other thing that's interesting is what this tells you is because of the Hall effect, I said this number might be 10, there's a significant current that's just flowing along the axis of the device, right? So the actual current path is kind of diagonally up that way, right? Because you got an X direction and Y direction both. And that one's not doing any good either, right? It's just flowing through an ohmic loss. So you don't get this for free, to extract the power. You have to pay attention to the Hall effect here. So what do you do to improve that? You don't want that happening. It's not doing any useful work. Well, very smart people realized quickly there were ways around this. You could just chop up that long electrode into a bunch of pieces, and that's what's shown here. And each one of these then, and the diagram here, by the way, I couldn't figure out a decent way to show it. So that's an electrode. The flow is going this way, and this doesn't have to be like an opening here or something, but I'm just trying to show there's an electrode with a wire that ducks around the back of the channel, and you put a load, something that you want to make power with, on each one of these. Well, that breaks up the X direction current, so the X flow of current is 0. Why does it do that? Anybody see? I wrote it at the bottom, right? Why does it do that? Just wake you up here for a second. Because there's nowhere for the current to go, right? You can't have an X flow of current because you can't just pile up in this end, right? So by breaking these things up, you don't have any more Hall current. And so Jx, the current flow in this direction, happens to be 0. And that lets you set a relation between these two quantities, right? Here and here. These two are now equal to get that to be 0. You can substitute that back in and then calculate the current that can flow in this direction. So if I go through and do that and just simplify the terms that are present there, the Y direction current comes out to be exactly the same as what I started with when I was ignoring the Hall current. As it should, because I got rid of the Hall current, right? So you think, oh, that's a good idea, because now I don't have to worry about that loss that was sort of plaguing the concept just by breaking up these electrodes. It seems like a reasonable thing to do. There are a few catches here, all right? Although you don't have any current flowing in this direction, let's see, where can I find my EX? Right here, the X direction electric field turns out to be huge, right? So now you have this big electric field running along the axis of the device, which if it's grounded somehow, it can actually then lead to an arc, which you don't want to do. That's not unsurmountable, but it's just a reality. And then there's another practical disadvantage that occurs with this idea of breaking up all the electrodes. Can you see it? What's the disadvantage if I have to break all the electrodes up? Anybody? You got a whole bunch of current circuits out there, right? Instead of maybe having just, I'm trying to run off to a transmission line, now I have a bunch of things I have to run independently, right? Because they can't communicate their current flows. Well, modern electronics, this probably isn't as bad of an issue as it was 20, 30 years ago. You could probably divide that up, but it is a consideration. So there's some disadvantages to doing this because you have to have all these individual loads. Again, people that thought about this very carefully realized, well, maybe there's some other ways I can get rid of all those extra loads, right? Instead of putting loads on these guys, I'll just short them out, all right? So if I short them out, then the voltage field running in the Y direction from here to here is 0 because I've shorted it on the back side. I'm not doing any work there, but in that instance then the net is 0 and the EY part of that thing is equal to the minus UB, you can solve for the currents and the voltages just like I did before, and then you have this open circuit voltage which exists from this end all the way around to this end. All right? So essentially what you're doing here is you're letting, you know, the load just exist over the two ends, and you're taking advantage of that long, you know, passage to give you a very high voltage to a single load. All right? And the open circuit voltage then is a lot larger than U times B. That's what we started with. So it's an interesting idea because it gets rid of all those different electrodes, and these guys are just shorted out. All right? That's not bad. Now there's a variant of this. Take a deep breath. Really hard for me to understand the flow field here until I sit down and thought about it. There's a variant that's really quite intriguing called a disk geometry, and I'm trying to show this here in 3 dimensions where the flow is coming in here and then it exits radially outward. All right, so it's flowing out in this direction. So if I look in the side of that thing and I look at the flow, this channel is the same one that I've got here, except it's part of a radial geometry. Okay, see, is it clear what I'm looking at? This is the cutaway view looking through this direction. This one is really interesting because there's a big practical advantage. Let's see how this actually works. The magnetic field now is pointing up through here. The flow is going that way. If I go U cross B, it actually pushes the current. You can put your hand out that way and try and do that. It actually pushes it around radially around the circumference of that annulus. All right? And so it's conducting through the gas along that path length. All right? And then I'm actually using that motion, which is a Hall current, and then I'm actually depending on that, so one more U electron cross B creates the voltage from here to here that drives the load, which is really a clever geometry. And you know, if you want to go home and practice your right hand rule and convince yourself, that's actually how it works. And it's quite impressive that it works that way, not just because it's a fun flow design, but because you only have 2 electrodes, right? These 2 rings, one here, well, one here and one here, right? So the practical advantage with this geometry is there's just 2 electrodes, all right? And the way it works, again, is the U of the flow across the B drives a current through the gas, and that current flowing, that electron velocity, interacting with the B, the UE cross B, then sets up a voltage running along between those 2 electrodes. Just a very clever idea. There are a lot of other people that have thought about designs that you can go look up in the literature. Each one has its advantages and disadvantages. Some of these things, though, have not been reduced to practice yet. Some have. Here's one more, and then we'll get on, maybe kind of leave behind some of the heavier math here. There's an intermediate approach between simply shorting all the electrodes and having discrete loads, and that is to actually slant the electrode connections. And the reason you do this, here's an example for a single electron that you're trying to get to flow directly here and eliminate that Hall flow back and forth. What you do is you actually slant the electric field by connecting diagonally, by connecting electrodes that have a diagonal relationship. So you slant the field to counteract that Hall flow, so the electrons are moving in response to a force from the x direction electric field and then a force from the Hall effect, and so they have a drag from their collisions, but they end up moving just straight up from electrode to electrode. And so because you slanted this, you might have 2 loads on there just to connect all the electric circuits up. So it's an interesting idea because it gets rid of the complications of the Hall effect, has a small number of connections, and in fact, it was reduced to practice when people ran one of these. Here's a photograph inside of an MHD channel, and you can see the slanted wall there. That's the electrodes running along the axis, or running along the flow axis of the device. The only problem is that balance only exists at one load factor, right? Because you change the load, remember the the Y-directed load across the thing is going to change from open circuit to fully loaded. And so you only have good efficiency at one load parameter. That's why I mentioned the load parameter before, because you can see it's going to change the nature of the electric field. But it is a viable contender for geometry for these devices. All right, that's enough a detailed electric field. We're going to look now at something probably more familiar to combustion engineers. What about the fluid dynamics? What about the hydrodynamics? I just put this slide together because I don't know about you, but I had a struggle understanding how exactly does the energy come out of this flow, right? How do you get the transfer from fluid motion into electric energy? So we're not going to, spend a long time deriving these. Oh, I got to hit one more time. I noticed in the notes, if you're following along there, I forgot to put a cross, and it will matter if you try and decipher this 20 years from now, right there and right there, because I unwisely forgot V as a volume has to be different from V as a voltage, all right? So just put a cross on the volumes so you can make a distinction. If you need to go back and read these notes again someday, you'll say, oh, yeah, he meant voltage, not volume. What was he thinking? So anyway, that fixes that. But let's just quickly take you through the physics of how this works. And I'm just doing sort of a 1D energy balance through a volume of fluid here. So you have this volume of fluid, and inside of there you have generation from this MHD effect, and you have resistance. So the resistance, the I squared R, the ohmic loss, is the area, the planar area of that, squared times the current density squared, that's the I squared, and the resistance is just the width of the whole channel, all right, divided by, again, area and the reciprocal of conductivity right there times that. And so you just put the numbers in there. It's volume, J squared over sigma. Per unit volume, then, there's the ohmic losses that occur as you flow electrons through that region. The electric power output that comes out of that volume, that's just, current times the voltage. So the area times the current density, the voltage is the electric field times the height. All right, so you put that together, and then per unit volume divided by volume, you get the current density times the electric field. That's the electric power output. And the way I put these notes together, you have to be very careful, in terms of actually dealing with vector products here, because these are really dot products when you look at full vectors. So that minus sign is important if you say it's power output. So you read that carefully if you decide to actually redo this, and you need to distinguish between am I generating or am I doing pumping, and take care with the signs. So that's the electrical part of the equation. The mechanical energy input to this volume, well, that's just the x body force times the x velocity u. So here's the x body force per unit volume. This is charges per unit volume, the charge, and then it's the velocity of those electrons, the fluid velocity plus their drift velocity, UE here, cross product with B, that's so-called Lorentz force. Only want the x quantity here, dot it with I, and then, here's the reduction of that, just do the algebra. Turns out it's the current density cross product of the magnetic field. And so for this 1D problem, mechanical energy input reduces to JB, U, and again the minus sign, just to do the bookkeeping correctly for work in the way I put this together. So if you just take 1, 2, and 3, there's the expression for ohmic losses, where now I've used my load factor. Remember I defined K a long time ago? I stuck that in there so I can get my current density in terms of K. There's the expression for ohmic losses, electrical power out, mechanical power that you're putting in. You can double check all that algebra. 1 and 2 obviously have to add up to 3. So here it is physically. You're pushing the gas down that tube, all right? It's full of electrons. As soon as they see motion relative to the magnetic field, they resist that, right, and try to start to move. That motion causes another interaction, the Hall effect, with the magnetic field that also opposes that. I'm accounting for all those right here to give you the mechanical power getting converted to electrical output. Okay, so there it is in like 30 seconds or less. If you get interested in this, just a handy way to get started to figure out, well, how does the work actually get converted? Because I just conceptually had a hard time with how the body force works. If you want to pursue this further, I mean, there are whole textbooks devoted to it. I've got one citation there. You can find many, many others you know, that'll give you the governing equations. So all I did was I covered the energy equation there a moment ago, and now if I treat J just for a 1D problem as a negative scalar, continuity doesn't look any different than what you see in, you know, conventional fluid mechanics. Momentum equation, I have this Lorentz force that's a source term for what is otherwise a familiar momentum equation. And then the energy equation, you have J, the product of the current density in electric fields. So that's another source term for energy, the negative of the output. So what happens again is this stuff is flowing. You're extracting energy out from the interaction of the magnetic field with those flowing electrons. And that's how you get the energy out of the device. So a lot of detailed math there, a lot of, you know, discussion, but here's the physics. I want to just see if we've connected with you today on some of this. What happens right where you're trying to get the electricity out at the electrode? What has to happen to the current density right at that point? Just look at the diagram. Is it obvious? It's just got to concentrate, right? So the current density is going to go up right as I get near that electrode, and it's sitting there with this, you know, flow that's pushing along, that's, you know, helping respond to this magnetic field, and I'm driving the current density up. So you've got concentrations right in that region that are not uniform. All right, and this is where it starts to become very complicated, because the conductivity in this region is dropping right in this region due to temperature loss right to there. You know, I'm pushing on the flow, and I'm losing conductivity right at that point. And so you have the potential for instability in the flow right there, right? You also have potential instability in the conductivity through the region, which can lead to arcing right at that point. So a lot of the action is what happens right in this region, right near the electrode. And that's, we're actually starting to do some simulations of flow. We haven't done the electrical part yet in that region, just so we can understand what's happening right at that point. Well, I've said the gas has to be conductive, this is a huge subject, but we'll take a look here at conductivity in this gaseous media. It's 4:25. You guys need a break, I can tell. I'm sorry, I'll keep talking all day. Come back at 4:35. I'm sorry, I didn't realize I ran right through the break there. We'll jump right back into this. Sorry. You should have interrupted me.